The January 20th paper in the Astronomical Journal is fueling our interest in planetary exploration and stimulating a healthy debate that's part of the scientific process. I couldn't be more pleased about what's happening. It's all about starting the process that could lead to an exciting result. It is not, however, the detection of a new planet. It's too early to say with certainty that there is a so-called Planet X out there. Beyond Neptune's orbit, in the farthest reaches of our solar system, something strange is unfolding. A mysterious force appears to be influencing icy objects, causing them to cluster in unusual orbits that can't be explained by the gravitational pull of the known planets. Scientists believe this phenomenon could be the result of a massive hidden planet, often referred to as Planet 9. First proposed in 2016, the idea of this elusive world has captivated astronomers. Interestingly, this wouldn't be the first time a planet was predicted through mathematics alone. Both Neptune and Pluto were discovered after their gravitational effects were calculated long before they were observed through a telescope. Astronomers first noticed irregularities in Uranus's orbit, and later unusual patterns in the orbits of Kuiper Belt objects, which led to the discovery of distant worlds. Now, a century later, we find ourselves in a similar situation with Planet 9, continuing the fascinating tradition of using mathematical predictions to uncover hidden celestial bodies. Some researchers speculate that Planet 9 might have been a rogue planet captured by the sun's gravity, while others propose it formed from the same disk of gas and dust that created the rest of the solar system. If it exists, Planet 9 is estimated to be 10 times the mass of Earth and orbit the sun at an astonishing distance of 400 to 800 astronomical units, 400 to 800 times the distance between Earth and the sun. Astronomers are eagerly searching for evidence of this elusive planet, employing powerful telescopes and advanced computer models to trace its gravitational influence and piece together its mystery. After years of observing the sky, solving intricate equations and running sophisticated computer simulations, astronomers now have some of the strongest evidence yet for the existence of Planet 9. This discovery adds a thrilling new chapter to the mystery of our solar system's hidden planet. But what exactly have researchers uncovered in their search for Planet 9? And if we can detect exoplanets located hundreds of trillions of miles away, why has spotting this potential giant right in our cosmic neighborhood been so difficult, even with some of the world's most powerful telescopes? Most intriguing of all, if Planet 9 does exist, how did it end up so far from the rest of the solar system? Before we dive into the details, don't forget to subscribe for regular updates on the latest space discoveries. While the idea of Planet 9 was first proposed in 2016, its story actually began much earlier, shortly after the discovery of Uranus in 1781. Over the years, astronomers noticed something unusual. Uranus wasn't moving exactly as their calculations predicted. It seemed to speed up and slow down in its orbit, suggesting the presence of an unseen force influencing it. In the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently hypothesized that these irregularities could be caused by the gravitational pull of an unknown planet. Using complex mathematics, they predicted the location of this hidden world, a bold proposition based entirely on calculations rather than direct observation. Le Verrier sent his predictions to Johann Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant pointed their telescope to the region of the sky Le Verrier had pinpointed. To their amazement, they discovered Neptune on their very first night of searching, remarkably close to where the calculations had predicted. This groundbreaking achievement marked the first time a planet was discovered through mathematical prediction rather than chance observation. After Neptune's discovery, astronomers believed they had completed the inventory of the solar system's major planets. But as they tracked Neptune's orbit, they noticed subtle, persistent deviations, similar to those observed with Uranus, hinting once again at the possible influence of another hidden object. Building on the success of using gravitational influences to predict Neptune's existence based on Uranus's orbit, astronomers wondered if the same method could uncover yet another distant planet. This search ultimately led to the discovery of Pluto on February 18, 1930. Clyde Tombaugh, a young astronomer at the Lowell Observatory, spotted a faint distant object moving against the backdrop of stars, confirming the existence of a new celestial body. Initially celebrated as the long-sought Planet X, Pluto was later found to be far smaller than anticipated. Its mass was insufficient to explain the gravitational anomalies observed in the orbits of Uranus and Neptune. This suggested that something even larger and more distant remained undiscovered. Beyond Neptune's orbit in 1951, Dutch-American astronomer Gerard Kuiper proposed a groundbreaking idea. Pluto wasn't alone. He theorized the existence of a vast population of icy objects beyond Neptune, forming what we now call the Kuiper Belt. Pluto, as it turned out, was just one of many such objects. Confirmation of Kuiper's hypothesis came decades later in 1992, when astronomers David Jewett and Jane Liu discovered 1992 QB1, the first identified Kuiper Belt object, KBO. This groundbreaking observation provided direct evidence of a region populated by countless icy bodies, fulfilling Kuiper's prediction and reshaping our understanding of the outer solar system. The discovery of 1992 QB1 was quickly followed by the identification of hundreds more Kuiper Belt objects throughout the 1990s and 2000s, firmly establishing the Kuiper Belt as a major component of our solar system. As more objects were found beyond Neptune, the term trans-Neptunian objects, or TNOs, was introduced to describe all celestial bodies orbiting the Sun at an average distance greater than Neptune's orbit, approximately 30 AU. With a growing catalog of known KBOs, the idea of a single massive planet X began to lose traction. Astronomers proposed that the combined gravitational influence of many smaller bodies in the Kuiper Belt could account for the observed irregularities in Neptune's orbit. However, a surprising discovery in 2003 reignited interest in the search for a hidden planet. Astronomers identified Sedna, a distant TNO with an unusually elongated orbit. Sedna's aphelion, the farthest point in its orbit from the Sun, is an astonishing 937 AU, making it one of the widest orbits known in the solar system. This unexpected finding shifted the focus back to the possibility of a massive unseen Planet 9, influencing the orbits of distant objects like Sedna. That's 31 times the aphelion of Pluto, and 19 times that of Neptune. Sedna's perihelion, or closest approach to the Sun, is just 76 AU. In contrast, Pluto's entire orbit averages only 248 years, while Sedna takes an incredible 11,400 years to complete one orbit around the Sun. This is not only unusual but also raises two major questions. First, if Sedna formed in its current location, it would suggest that the Sun's protoplanetary disk extended to at least 75 AU, an upper limit far beyond what is typically accepted. Second, for Sedna to have formed through the accretion of smaller bodies, its original orbit would have needed to be nearly circular. A highly elliptical orbit like Sedna's would have resulted in violent collisions, preventing the aggregation of material necessary to form a large body. This implies that Sedna's elongated orbit must have been shaped by a gravitational interaction with a massive object after it formed.